Okay, let's look at the next usual case of partial fractions. I think I'll do this in 2 short videos. It's the case of a repeated linear factor. I've got the integral of a rational function. The denominator is a linear factor times a linear factor squared, or you would call that a repeated linear factor because it's like x minus 2 times x minus 2. This is going to be a little different from the previous case. First thing to check is the degree of the numerator here is 2. The degree of the denominator, if I did multiply this out, it's helpfully factored for me, would be x cubed. So there's no long division necessary. If this was like an x to the x cubed or x to the fourth, something like that, you'd have to do a long division first. But we're avoiding that right now. So what's the partial fractions expansion? What's the form of the partial fractions expansion? It is going to be a mystery number. Remember, these capital letters are always just numbers, no x's. They're unknown coefficients, but they are not variables. They're nothing to do with x. It's going to be somewhat similar to what we had before. Unknown coefficient over x minus 3. And it's going to have an unknown coefficient over x minus 2 quantity squared. But you also need a coefficient over x minus 2 just to the first power. Various ways to see why you need that. I don't think I want to go into it in detail, but one thing you could just observe is that if I started with this, with like a equals 7, b equals 2, c equals minus 12 or something like that, and you did common denominator, you'd get something like this. So if you start with this, how do you know it didn't come from something with an a b, and a c, all non-zero? So you really are going to need all three of these terms. Next step is totally identical. It's almost always the same thing. Clear denominators. We don't really like fractions. We're talking about fractions, but we'd really rather deal with polynomials. You multiply by the denominator on the left, and things clear out and get some cancellations. You get them on the right. Now we're going to do a mix of the two previous methods. The evaluation strategy that I showed in the second part of last time is very powerful. Won't get us all the way there, but it's a good start. You plug in x equals any root of the polynomial, the denominator you started with, and those should be showing up here as really obvious good ideas to plug in for x. Again, the idea is that this is an equality of functions of x, and it should be true for any specific value of x. So that's going to be, when x equals 2, the left-hand side, it turns out to be 10. Pretty easy check. The a multiplier goes to 0. The b multiplier goes to 0, and you just get c times minus 1. Ooh. Oh, okay, so c equals minus 10. So boom, you're going to get one of your coefficients just like that. Okay. X equals 3, another good thing to plug in. Now, once again, the polynomial multiplying b dies, and the multiplier for c dies. Now what lives is a. Oh, what's the left-hand side? 2 times 9, 18 plus 2 is 20. And there you get a times 3 minus 2 quantity squared. That's just 1, so a is 20. Okay. That's going to be it. Unfortunately, we couldn't get b because no matter what you plug in, either 2 or 3 of these very special values that kill some of the coefficients, b is always going to die. So that's too bad. Okay. Various ways to proceed from here, but I'm going to show you the strategy of going back to the equating coefficients. So maybe not quite as elegant as some other methods, but it has the advantage of being straightforward and giving you a double check on your answer. Okay, so we just go ahead and we plug in the known values for whatever we found. That's often a place that students get stuck, is when they're solving for multiple variables and they find a value for the variable, then they might go back to a previous equation and not realize that is now a known number. A is definitely 20. C is definitely minus 10. I put those in. Then I start expanding that out. Ooh, and I didn't finish that. That's okay. That's about where I wanted to be. Just expand it out carefully. Okay, so we get 20. I expanded it, and then I'm collecting 20 plus b, and that's all the x squared coefficient, plus minus 80 minus 5b minus 10, that's all the x coefficient, the linear term, and then plus, let's see, 80 plus 30, I might as well add that, that's 110. I'm going to put this in parentheses to make clear it has its own role. And what else? Oh yeah, plus 6b. Everything that does not have an x in it at all. These should be equal as functions of x squared. They're polynomials in x squared. Let me make this really explicit. Ooh. And therefore the coefficients should be equal. 2 should be 20 plus b. 0 should be minus 80, etc., etc. And 2 should be 110 plus 6b. Okay, so I should be able to pick any one of those, since I've only got one variable left, pick any one of them and solve for b. If I have no chance of making any mistakes, I could just get that b and proceed. But I might as well use it as a double check. So let's see. Let's use 2 equals 20 plus b to actually find b. B equals minus 18. Okay. And then I'm actually going to double check. Okay, let's see. Minus 5b minus 90. What's that going to be? Oh, minus 5 times minus 18. Hey, that's 90 minus 90 equals 0. In fact, when I did a previous version of this video, I did make a mistake, and it checked. I found that mistake by doing exactly this second calculation. I didn't want to show you that, though, so I'm redoing it. Okay. All right, and then one more check. 110 plus 6 times minus 18. Okay, that's turns out to be 110 minus 108, and boom, that's 2. Okay, so these are just double checks to make sure it's all working. So it's pretty good to do that. Okay, even though there's a little bit of work and you have to make sure you're expanding and collecting carefully. All right, so we've got b equals minus 18. All right, so now let me just go back and copy and paste, and I think I'll save the actual integration part for the second part of the video. Okay, oh, let me just get my original one there. Okay. And so here's my expansion. And a was 20. And c was minus 10. And b is minus 18. Okay. And so the integral, let me just write it out, from, I think it was going 4 to 5. Is that what I wanted? Yeah. Is the integral from 4 to 5 of all this stuff. And of course, the next thing we're going to do is go ahead and break that up as much as we need into separate integrals if separate techniques are necessary. And for all of them, slightly different things happen. And so we're going to do that in the next part.